Let's investigate the quantum algorithm for period finding and compare it to the order finding subroutine of Shor's factoring algorithm. We will see many similarities with the phase estimation procedure. Consider a periodic function f. The goal of the period finding quantum algorithm is to find the minimum positive integer r such that f of x plus r is equal to f of x. In the context of period finding, r is the period of this periodic function f. And it's very important that we specify that it is the minimum positive integer that satisfies this condition, because we might be able to find larger positive integers that also satisfy this condition. And those positive integers might be integer multiples of r. So we're dealing with the minimum positive integer that satisfies this periodic condition. So now we have a statement of the problem. This r is what we're looking for. Now let's construct a quantum algorithm which can allow us to find r. So step one is initialization. We're going to initialize two registers of qubits. The first register will be initialized in the state 0, and the second register will also be initialized in the state 0. By convention, I'm putting the first register on the left and the second register on the right. This 0 is shorthand notation. So we don't mean that we're not talking about the computational basis state of a single qubit. We're talking about initializing an entire register of qubits, all in the state labeled by 0. So we just have a string of zeros. And the number of zeros over here corresponds to the number of qubits in the register. So we're going to use the letter m to denote the number of qubits in the first register. And we can use capital L to denote the number of qubits in the second register. So step number 2 is creating a superposition in the first register of qubits. So step 2 involves applying the Hadamard gate to all of the qubits in the first register. So that is going to produce a normalization coefficient of 2 to the minus m on 2. So this m is the number of qubits in the first register, times a sum over some index k starting from 0 and going up to 2 to the m minus 1. So we have to subtract 1 over here because we are starting from 0. And 2 to the power of m, that is the dimension of the Hilbert space for this first register, which consists of m qubits. And this is the normalization factor out the front. Then we're going to have ket k, and this index k is a label for all of the computational basis states for the first register. And the second register is going to remain unchanged. So it's still going to be in the state 0. Now the next step is going to involve implementing a black box. So let's write down what that black box is going to do. We're going to consider the starting register states as ket x, ket y. And this black box is going to map this state over to the state ket x, ket y, and then we have addition modulo 2. That's what this sign represents. So we have addition mod 2, and then we have f of x. So this is what the black box is going to do to this initial state. So we have x and y. These are labels for the states of register 1 and register 2. And when we apply this black box procedure, we get this output over here. So you can see that this x over here, the contents of the first register, is being used to modify the contents of the second register. And we're putting x inside this function f. So that's the periodic function we're dealing with. And then we're using addition modulo 2 to combine y and f of x. And that's going to be the label for this state of the second register. Consider the special case where we set y equal to 0. That's going to produce ket x, ket 0, and this is going to get mapped to ket x, and then over here, we're just going to have ket f of x. So all we've done is set y equal to 0. And the reason I've chosen to demonstrate this special case over here is because this is what we're dealing with in step 2. And then when we go from step 2 to step 3, we're going to apply this black box procedure. So let's see what that does. So step 3, I'm going to write over here, involves applying the black box. So we're still going to have the superposition. We have the normalization coefficient of 2 to the minus m on 2. Then we have the sum over k going from 0 up to 2 to the m minus 1. We have ket k, but then because we've applied the black box, the state of this second register is no longer 0. Now it is f of k. So this is what we've done. We have used this black box procedure to create this superposition of states. So k is the entry in this first register. And the contents of this first register are being used as an input. And we're putting that inside this periodic function. And then f of k is being used to construct the contents of this second register. And all of this is being summed over the index k. So we have a superposition of many states. In fact, we have 2 to the m states. That's the dimension of the Hilbert space for the first register. That's because m is the number of qubits in the first register. So now that we have we've just created that. We've gone from step 2 to step 3, implementing this black box procedure. Now let's make some observations about this state over here. So we can express f of k, this state, in a different way. We can express ket f of k as r to the minus 1/2 times the sum over some index s going from 0 up to r minus 1 of e to the 2 pi I k s on r ket f hat of s. And let's see what this object is over here. So let's consider this state ket f hat of s. We can write it in a similar format. We can write this as r to the minus 1/2 times the sum over the index k going from 0 to r minus 1 of e to the minus 2 pi I k s on r. And then we're going to have ket f of k. So the format of these two equations is actually of the Fourier transform. So we have this Fourier transform format, and when k is a fixed value, s is acting as the index in this sum. So we're summing over s. And when s is a fixed value, we're summing over the index k. Another notable difference is the sign in this complex exponential. Here we have a plus sign, and here we have a minus sign. So that is how you convert between the states f of k and the states f hat of s. So now that we have this relationship, let's substitute this relationship into this expression in step 3. So let's do that over here. We're going to have an approximate equality. And the reason there's an approximate equality with this step is because r might not exactly divide 2 to the m. So 2 to the m might not actually be an integer multiple of r. That's why we have to put an approximate equality over here. So 2 to the m, that's a power of 2, and r does not have to be a power of 2. So that is the reasoning for this approximate equality. Now, what we're going to have is the normalization coefficient of r to the minus 1/2, 2 to the minus m on 2. Then we're going to have two sums. We're going to have a sum over this index s going from 0 to r minus 1. And then we're going to have a sum over the index k. And k goes from 0 to 2 to the m minus 1. Then we're going to have these complex exponential factors. That's e to the 2 pi I k s on r. And then we will have ket k. And we have switched from the states denoted by f of k to f hat of s. So we have ket f hat of s. And now that we have this format, we can apply the inverse quantum Fourier transform to the first register. And what is that going to give us? It's going to give us step 4. So step 4 will produce r to the minus 1/2 times the sum over the index s going from 0 to r minus 1. Then we're going to have ket s on r tilde. This tilde means we have an approximate value for s on r. And then we're going to have ket f hat of s. So this is very similar to what we saw when we were constructing the order finding subroutine of Shor's factoring algorithm. We also had these 4 stages: initialization, creating a superposition in the first register, applying this black box procedure, then using this approximate form over here, and finally applying the inverse quantum Fourier transform to the first register to produce this final state. And when you measure this state, you will get a value of s on r tilde, and it will have one of these values of s. So we don't know which s we're going to get, but we will get one of the values of s going from 0 to r minus 1. So what does that actually mean? What is this s on r tilde telling us? So s on r tilde can be thought of as the phase in a phase estimation procedure. You see that s on r appears over here in exactly the same place where we would find it in the phase estimation procedure. So that's why I'm going to call this quantity s on r tilde phi of tilde. And when we actually measure this value, what we're going to get is a string of bits. And we can call those bits phi 1 dot 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 up to phi m. Why is it m? That's because m is the number of qubits in the first register. So that's the same first register that we initialized to all zeros in step 1. And in this final step, we have these values over here for the labels of the states in the first register. So now that we have this scenario, we can see that this is actually equivalent to 2 to the power of m times 0.phi1 dot 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 all the way up to phi m. What do we mean by this notation? This is not a decimal. We're not dealing with base 10. We're dealing with binary. This is base 2. So this value after the point is actually corresponding to 1/2. And then we're going to have a quarter, and then 1/8. And we're going to keep going all the way up to this mth term. So if we take this fractional value, which is less than 1, and we multiply it by a factor of 2 to the m, that's going to shift this m units to the left, and it's going to move it all the way left of this point. And so what we're going to get is a positive integer. So this is a positive integer written in binary. It's an m-bit positive integer. And each of the bits in this string are going to be the results of measurements when we measure all the qubits in the first register. So we can write this in another way. S on r tilde is a very good approximation or an estimator for 2 to the m times s on r. So what are we actually measuring? We're measuring the quantity s on r multiplied by a factor of 2 to the m. And when we measure this value, what we actually get is a positive integer. So it's an m-bit approximation. We only have m bits in this measurement. And when we have this value, what we can do is use the continued fractions algorithm to extract the value of r. This is very similar to the order finding algorithm. One thing that I want to clarify is how we're representing this in binary. I'll write this out explicitly for the value k. So k is the index which we used in these steps, and I'll write k as a string of bits. k1 ... all the way up to km. So k is an m-bit number. And what does this actually mean? Well, we can write this in summation notation. This is the sum over some index, let's call it q, going from 1 up to m. And we're going to have k sub q times 2 to the m minus q. So this first bit over here, k sub 1, that corresponds to q equals 1. We have k sub 1, and that's multiplied by 2 to the m minus 1. And what about the last term, k sub m? That corresponds to q equals m. We will have k sub m times 2 to the m minus m, and that is 2 to the 0. So that's actually the ones bit. This last bit over here, that is the ones bit. And if we multiply this entire number by a factor of 2 to the minus m, we're going to get rid of this 2 to the m. So we will just have 2 to the minus q in this expression. So that is how you translate between this expression and this expression over here. It's a factor of 2 to the m. And that corresponds to shifting the point. All you're doing is shifting the point by m units, either to the left or to the right. That depends whether there's a plus sign over here or a minus sign. You can move this factor of 2 to the m to the other side of the equation, and you would have to put a minus sign over here. So that is just some more details as to how we are constructing this notation for these binary numbers. Okay, so now that we have understood the general procedure for period finding, we can look at a special case. So let's consider the special case, which is actually order finding, the problem of order finding, which appears as a subroutine of Shor's factoring algorithm. So let's consider the example, e.g., f of k equals a to the k mod n. So this is an example function. We have a periodic function here in general, and we have a general algorithm that can find the period of this function. And now we're considering a specific function. And this function takes in the input k, and it spits out a to the k mod n. What is n in this context? N is the semi-prime integer that we are trying to factor using Shor's factoring algorithm. And a is a number which is co-prime with n. So a is also a positive integer. It is between 1 and n. And it does not have any common factors with n. Or in other words, the greatest common divisor of a and n is equal to 1. So this is the problem of order finding. And how do we actually go from the problem of period finding to the problem of order finding? Well, if we take this format over here, we can write this as equal to a to the k plus r mod n. And that means that this is equal to f of k plus r. So we have this format of a periodic function, and we're just stating that a to the k is the same as a to the k plus r mod n. So that actually means that a to the r is the same as the multiplicative identity. So it's equal to 1. So we can take this problem over here, and we can turn it into the order finding problem. And I'll write that over here. We can take that and we can identify that it is the problem of finding the minimum positive integer r such that a to the r is equal to 1 mod n. So you can see that this is the requirement that we need for this equality to work. We need to be able to get rid of this a to the r mod n factor over here. And we can use exponential laws to break that up. So this is a general problem of period finding, and we're applying this period finding problem to a specific function, and we're actually translating that into the language of order finding. We're finding the order of the element a mod n. And now that we have this procedure, let's give some insight into how to actually perform this black box procedure. So when we were doing order finding, we found that there are actually multiple ways to initialize and then perform this black box, which takes us from step 2 to step 3. So let's see how we could actually do it. So one possible option is to initialize in the state 0, 0. How would we do that? Well, we could consider a black box which takes the initial state, ket k, ket j, and maps it to the state ket k, ket a to the k plus j mod n. So here we have addition. We're adding j to a to the k. And k is the entry over here. It is the contents of the first register. And if we set j equal to 0, that's going to give us k, 0, and that's going to get mapped to k, and then we'll have a to the k plus 0. 0 is the additive identity, so that doesn't change anything. Then we have mod n over here. And this is what we want. This over here, this is f of k. That's the function we're dealing with. It's the periodic function that is specific to the problem of order finding. So this is one way to do it. Another way to do it is by initializing the state in this second state in the state 1. So we could also do that. And we need to define the black box procedure slightly differently. So we can consider ket k, ket j getting mapped to the state ket k, then a to the k times j. So the difference here is that we're multiplying a to the k and j. So here we have addition, and here we have multiplication. And then if we set j equal to 1 in this, so the second register is initialized in the state 1, that's going to get mapped to k, and then we will have a to the k mod n. So we end up with the exact same state. So this is the same state that we end up with. But we started off with a different initialization procedure. Over here we initialized the second register in the state 0, and over here we initialized the second register in the state 1. And it's because the black box procedure is defined slightly differently. So the initialization depends on the black box, which takes us from step 2 to step 3. We still have to implement this superposition in the first register, but it is this state over here that goes along for the ride in step 2. So it depends on how we actually go from 2 to 3 to get this state. So either way, either of these choices will give us the correct state here at step 3. It's just a different definition of the black box procedure, which requires a different initial state to produce the correct output. So let's consider this initialization procedure. This is what we used in the order finding subroutine video for Shor's factoring algorithm. We started with 1, and then we ended up with this state over here. We can actually define a unitary operator that does this procedure. So let's elaborate on this state, a to the k mod n. So let's see the details. How does this actually work? We can identify that a to the k mod n is equivalent to a to the power of this sum. So k can be expressed as this sum of k sub q's times these powers of 2. And if we put this sum in the exponent, then we can use exponential laws to break that sum up. And then we can actually break this into the product of many terms. And there's going to be m terms. We have the product of m terms. And what are those terms going to look like? The first term is going to be a to the power of k1 times 2 to the m minus 1. So this is the q equals 1 term. And we're going to have all the intermediate terms being multiplied. And then the final term is going to be the q equals m term. And that's going to have the format a to the power of km times 2 to the power of m minus m, which is 0. So this is the same as 1. 2 to the 0 is 1. And all of this multiplication is being done mod n. And now this format, we can actually see that we can apply a unitary operator successively with different powers. And so this is going to be equivalent to u, this unitary operator, which I will define in a moment, to the power of k1 times 2 to the m minus 1. Then we have dot, 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 all of the intermediate terms that correspond to these intermediate factors. These are intermediate values of q between 1 and m. And then the final unitary operator is u to the power of km 2 to the 0. And the state that we're beginning with is the state 1. So the initialization of the second register is in the state 1. We're using this black box procedure. So if we start off with this black box procedure, we're going to be applying this procedure over here. So you can see that applying these controlled unitary operators, this sequence over here, to the initial state 1 is the same as modular exponentiation. So that is the name for this procedure. It is called modular exponentiation. And in the order finding subroutine of Shor's factoring algorithm, for us to go from step 2 to step 3, we have to implement modular exponentiation. Now let's elaborate on this unitary operator u. U takes the state j and it maps it to the state a times j mod n. And we investigated this unitary operator in the previous few videos. And we actually applied the phase estimation procedure to this unitary operator. And we used that to get values of S on R, or at least approximate values of S on R. So that's S on R tilde. And once we have these values, we can apply the continued fractions algorithm to extract R. So what have we seen in this video? We defined the problem of period finding. And the period finding problem is this statement over here. The goal is to find the minimum positive integer r such that f of x plus r is equal to f of x for some periodic function f. We went through these 4 main stages, which include initialization, creating superposition, then implementing this black box procedure, and finally performing the inverse quantum Fourier transform to the first register. And once we have this final state in stage 4, we can perform a measurement of the first register, and that will give us an estimator, S on R tilde. And then we can process this classically using a classical computer, and that's going to allow us to use the continued fractions algorithm to extract the value of R. And then once we understood this period finding problem in general, we looked at the specific case of period finding for this function, a to the k mod n. And we saw that we can translate this problem of period finding into the order finding problem, where we find the order of a mod n. And we looked at some different ways we can perform the black box procedure, which takes us from the state in stage 2 to the state in stage 3. And if we consider just this black box procedure, we can define a unitary operator u, which takes an initial state j and multiplies it by a mod n. And another important point to stress on is that we can interpret these f hat of s terms over here. These states are actually eigenstates of this unitary operator. So that's one interpretation for these states. So what we're doing when we have this approximate equality is we're rewriting this state in stage 3 in terms of eigenstates of the unitary operator. And now when we're dealing with these eigenstates, we introduce this extra summation over the index s, and we also introduce these factors of e to the 2 pi I k s on r. And this format is the format that is perfect for applying the inverse quantum Fourier transform. Because once we do that, we get this simple form, and we can just measure these estimators for S on R. So this is the period finding algorithm. And we're actually going to see that period finding and order finding are special cases of a far more general type of problem which can be solved efficiently using quantum algorithms. And those are called hidden subgroup problems. We will see many more types of these problems in later videos.